For most of human history, Pluto was nothing more than a smudge. Discovered in 1930 by Tombaugh, it remained a single point of light for 85 years, a faint speck that even the Hubble Space Telescope could render only as a blurry cluster of pixels. We knew its orbit, roughly its size, and almost nothing about its face. Then, on July 14, 2015, everything changed in a matter of hours. A spacecraft called New Horizons, no larger than a grand piano, swept past Pluto at more than 49,000 kilometers per hour and, for the first time, showed us a world. The images that came back stunned even the scientists who had waited 9 years for them. Here were mountains rising 3 kilometers high, made not of rock but of water ice frozen harder than granite in the cold. Here were vast plains of nitrogen ice, smooth and pale, cut into strange polygonal cells. And here, unmistakable, was an enormous bright region shaped like a heart, later named Tombaugh Regio in honor of the man who first found this distant point of light. The resolution was extraordinary. Some mosaics reached roughly 80 meters per pixel, sharp enough to trace individual glaciers flowing across the surface, sharp enough to reveal terrain that looked freshly sculpted. And that sharpness bred suspicion. Across the internet, viewers looked at these pictures and refused to believe them. The colors seemed too vivid. The surface seemed too clean, too crisp, too perfectly composed, as if an artist had painted it rather than a camera recording reality 4.8 billion kilometers away. How could a machine that small, flying that fast, past a world that dim, produce images this flawless? The accusation was simple. It looked fake. This is the central mystery we will unravel. The truth is stranger and more impressive than any conspiracy. Every mountain, every plain, every crater in those pictures is real, recorded during a flyby that lasted only a few hours. But to understand why the real can look unreal, we must first follow the impossible journey that made these images possible at all. The story of those images does not begin in 2015. It begins on January 19, 2006, at Cape Canaveral, when an Atlas V rocket lifted New Horizons off the launch pad and hurled it toward the outer solar system. It left Earth faster than any spacecraft before it, at roughly 58,000 kilometers per hour, crossing the orbit of the Moon in just 9 hours, a journey that took the Apollo astronauts 3 days. Speed was everything, because the target was almost unimaginably far. Pluto orbits at an average distance of about 5.9 billion kilometers from the Sun. Even at that blistering velocity, the trip would take nearly a decade. Mission planners needed a shortcut, and they found one in the largest planet of them all. In February 2007, New Horizons flew past Jupiter, threading close enough to steal a fraction of the giant's momentum. This gravity assist accelerated the craft by roughly 14,000 kilometers per hour and shaved 3 years off the travel time. As it passed, its cameras rehearsed for Pluto, photographing Jupiter's storms and its volcanic moon Io spewing plumes into space. Then came the long silence. For most of the following 8 years, New Horizons slept. To preserve its systems and its plutonium power source, engineers placed it in hibernation for stretches lasting months at a time, waking it only for periodic checkups. It coasted through the dark emptiness beyond Jupiter, past the orbit of Saturn, Uranus, and Neptune, a lonely machine carrying a small canister of Clyde Tombaugh's ashes toward the world he discovered. By the time it approached its target, the signals it sent home took about 4.5 hours to cross the void, traveling at the speed of light. Commands could not correct anything in real time. The spacecraft had to execute its flyby autonomously, following a sequence programmed long in advance. 9 years of engineering, patience, and calculation all converged on a single window measured in hours. And when that window opened, everything depended on 2 remarkable instruments: cameras built to capture faint light at the edge of the solar system. To understand the pictures, we must understand how those cameras actually saw. New Horizons carried 2 eyes to Pluto, and neither worked the way most people imagine a camera does. The first was LORRI, the long-range reconnaissance imager, a telescopic camera with a 20.8 cm mirror designed to resolve fine detail from enormous distances. The second was Ralph, a combined instrument holding both a color imager and an infrared spectrometer, built to map composition and temperature across the surface. Together they gathered the light that became history. But here's the crucial fact that fuels so much confusion. LORRI does not see in color at all. It is a panchromatic imager, meaning it records only brightness, shades of gray across a wide band of the visible spectrum. Its detector counts photons striking each pixel and translates that count into a value from black to white. The raw images LORRI returned from Pluto were grayscale, sharp, monochrome portraits with no color whatsoever. This is not a limitation, it is a design choice. A panchromatic sensor collects far more light than a color one, which is essential when your subject is dimly lit by a sun that appears 1,000 times fainter than it does on Earth. At Pluto's distance, sunlight is roughly 1,000th of what we receive, a permanent, deep twilight. To capture detail in that gloom, the camera prioritized sensitivity and resolution over color. Color came from Ralph. Its imager carried separate filters, blue, red, near-infrared, and more, photographing the same terrain through each one in turn. Each filtered image was, again, a grayscale record of how much light passed through that particular filter. Only later, on Earth, could scientists combine these separate channels, assigning each to a color and layering them together to reconstruct hue. So the pictures that circled the globe were not snapped like a photograph on a phone. They were built. Grayscale data from LORRI provided the crisp structure. Filtered data from Ralph provided the color information. Everything had to be transmitted, received, and reassembled by human hands and software. This is the first key to the mystery. But the raw data itself depended on timing so precise it borders on the miraculous, a window that opened for only a few hours. The heart of the mission lasted barely a day, and the sharpest images came from a window only a few hours wide. On July 14, 2015, New Horizons made its closest approach, passing about 500 kilometers from Pluto's surface and roughly 800 kilometers above it at the moment of nearest imaging, depending on how the distance is measured from center or surface. At that range, and at that speed of nearly 14 kilometers per second, the geometry was brutally unforgiving. Consider the problem. The spacecraft was hurtling past its target so quickly that Pluto's face was rotating and shifting in the field of view minute by minute. There was no orbit, no second chance, no slowing down. Everything had to be captured in a single pass, with the cameras pointed by precise commands loaded weeks earlier. A pointing error of a fraction of a degree, or a timing slip of a few seconds, would have sent the sharpest frames staring into empty space. Yet the sequence executed almost flawlessly. During those hours, LORRI captured images at resolutions reaching roughly 80 meters per pixel across parts of the surface. To grasp that number, imagine photographing an object smaller than a soccer field from the distance between cities. The craft resolved features the size of buildings on a world nearly 6 billion kilometers away, a world we had known for 85 years only as a moving dot. This is precisely the sharpness that makes viewers suspicious. Everyday photographs are limited by atmosphere, by haze, by the shake of a hand. But space has no air to blur the view. LORRI's crisp optics, combined with the astonishing proximity of the flyby, produced images so clean that they lack the imperfections our eyes expect from a photograph. There is no atmospheric distortion softening the edges, no dust on a lens, no motion smear where the sequence worked as planned. The clarity itself reads as artificial. And when those pixels finally resolved into terrain, they revealed something no one had predicted. A landscape far too young, too smooth, and too alive to belong to a frozen, dead world at the solar system's edge. When the surface came into focus, the defining feature was impossible to miss. An enormous pale region shaped almost exactly like a heart, spanning about 1/600 kilometers across. Scientists named it Tombaugh Regio, honoring Pluto's discoverer. But it was the western lobe that rewrote the textbooks. A vast, smooth basin called Sputnik Planitia, roughly 1,000 kilometers wide, filled with frozen nitrogen. This plain was unlike anything expected on a world so cold and so old. Its surface was broken into strange polygonal cells, each tens of kilometers across, bounded by shallow troughs. These cells are the signature of convection. The nitrogen ice, warmed faintly from below, rises in the center of each cell, spreads outward, and sinks again at the edges. A churning motion so slow it takes perhaps 500,000 years to complete a cycle, yet fast enough to erase craters entirely. That is the astonishing part. Sputnik Planitia has virtually no impact craters. In a solar system 4.5 billion years old, bombarded constantly by debris, an uncratered surface means a young surface, one resurfaced within the last 10 million years, geologically yesterday. A world thought to be a frozen relic turned out to be actively reshaping its own face, surrounding this restless plain rose mountains that stunned geologists. Rising up to about 500 meters, comparable to peaks in the Rockies, they could not be made of frozen nitrogen, methane, or carbon monoxide. Those ices are far too soft to stand so tall. The only material rigid enough at Pluto's temperature of around minus 230 degrees Celsius is water ice, which at that cold behaves like solid rock, forming the bedrock of the entire world. Glaciers of nitrogen appeared to flow between these water ice mountains, spilling into the plains like ice streams on Earth. It was a landscape of towering ranges, flowing glaciers, and a beating, convecting heart, dynamic, complex, and utterly real. And yet, when the world saw the colors layered onto this terrain, the disbelief only deepened. Those vivid tones seemed invented, painted on. To answer that charge, we must confront the truth about color. Look at the most famous portrait of Pluto, and you will see a butterscotch world blushing with rust and cream. Then look at another, and the same surface glows in electric blues, turquoise greens, and pale yellows. Both are called real photographs. Both are correct. To understand how that can be true, you must abandon the idea that a camera simply records what the eye would see. The Ralph instrument aboard New Horizons captured light through separate filters, sampling narrow bands of the spectrum one at a time. Its MVIC channel recorded blue, red, near-infrared, and a methane absorption band. None of these individual frames is a color photograph. Color is assembled later by mapping each filtered exposure onto the visible palette. In the natural color version, Pluto looks much as a human traveler would perceive it, a muted tan globe, softly divided, more beige than dramatic. That subtlety is the problem. The differences between ices, the boundaries between regions, the faint chemistry painted across Sputnik Planitia are nearly invisible to unaided eyes. So scientists stretch the data. In enhanced color images, they exaggerate the separation between wavelengths, pulling apart shades the eye would blur together. A region rich in tholins, the reddish organic compounds formed when sunlight breaks apart methane, becomes vivid orange. Nitrogen ice plains turn ghostly white or pale blue. The false color composites go further still, assigning colors to non-visible bands so that surface composition becomes readable at a glance. This is not invention. Every hue traces back to a measured photon, a specific filter, a real reflectance. The colors are amplified, not fabricated. It is the same technique that turns a medical scan into a map a surgeon can read. What looks impossibly saturated is simply honesty made legible. And yet this is precisely why so many viewers recoil. A world that glows like a painted marble seems designed rather than discovered. But the geology beneath those colors is stubbornly real, recorded in reflected sunlight from 4 billion kilometers away. The palette can be adjusted. The shapes cannot. Which raises the next question. If the color is layered on afterward, how is the underlying image itself constructed, and why does the finished surface look so unnervingly seamless? The single perfect image of Pluto that circulates online was never captured in a single click. It is a mosaic, a quilt of dozens of separate exposures woven into one continuous face. During the flyby, Laurie and Ralph did not photograph the whole disk at once at full resolution. Instead, they swept across the surface in strips, capturing narrow frames as the spacecraft raced past at more than 14 kilometers per second. Each frame recorded a different patch of terrain taken at a slightly different angle, a slightly different instant, under a slightly different illumination. To build the famous portraits, imaging specialists at the Johns Hopkins Applied Physics Laboratory aligned these fragments, pixel by pixel. They matched craters, ridges, and the sharp shoreline of Sputnik Planitia across overlapping frames, then corrected for the changing geometry as Pluto rotated and new horizons flew by. The highest resolution mosaic, threading together strips at roughly 80 meters per pixel, reveals a band of terrain stretching across the encounter hemisphere with almost surgical clarity. This assembly process is where suspicion takes root. When exposures are blended well, the seams vanish. There is no visible stitching, no obvious break where one frame ends and another begins. The lighting has been balanced so shadows fall consistently. The result is a surface so uniform, so evenly lit, that it looks rendered rather than recorded. To an eye trained on ordinary snapshots, that uniformity reads as artificial. But the seamlessness is a triumph of alignment, not a lie. Every ridge in the mosaic exists in the raw frames beneath it. Every mountain of water ice, every pit in the nitrogen plains can be traced back to an individual exposure with a timestamp and a pointing angle. The mosaic does not add terrain. It only removes the gaps between glimpses. What feels too clean is really just the absence of clutter, the erasure of the boundaries our brains expect to see. Yet even after these images were composed, the story was far from finished. For all their apparent instantaneous perfection, these pictures did not arrive on Earth in a burst. They trickled home, one fragile packet at a time, across a distance that punished every bit of data. The flyby lasted only hours. The delivery took 16 months. This is the detail almost no one anticipates. New Horizons gathered far more information than it could possibly send home quickly. During the encounter, the spacecraft stored its images and measurements on solid-state recorders, roughly 16 gigabytes of data, capturing everything before slowly transmitting it back across the solar system. The reason for the delay is distance, and distance is merciless. Pluto sat about 4.8 billion kilometers from Earth. Even traveling at the speed of light, a radio signal needed roughly 4.5 hours just to reach home. And the signal itself was faint, almost beyond belief. By the time New Horizons transmissions arrived at NASA's Deep Space Network antennas, the received power was measured in fractions of a billionth of a watt. To recover data from a whisper that week, engineers accepted a punishingly slow transmission rate, often only 1 to 4 kilobits per second. At that pace, a single high-resolution image could take hours to arrive. The full archive could not possibly stream down in days or weeks. So the data came in a deliberate sequence. The most tantalizing images arrived first, in the days after July 14, 2015, revealing the heart and the mountains to a waiting world. But the complete dataset, every stored frame and spectrum, dribbled back piece by piece throughout the following year. The final bits of the Pluto encounter did not reach Earth until late October of 2016, more than 15 months after the closest approach. This slow trickle shaped public perception in a strange way. Because the sharpest, most polished images appeared early and dramatically, they arrived without the visible mess of raw incoming telemetry that ordinary viewers might expect. The public saw finished portraits, not the grinding machinery behind them. That gap between the effortless-looking result and the brutal effort required to obtain it only deepened the suspicion. If gathering these pictures was so hard, why do they look so easy, so flawless, so unreal? The answer lies not in the technology, but in us, and in why our minds distrust the very thing that proves the images are authentic. We distrust perfection because our world rarely offers it. Human photographs come cluttered with motion blur, lens flare, uneven light, and the accidental mess of everyday reality. So when we see Pluto, rendered with clean edges, balanced illumination, and vivid, readable color, some instinct whispers that it must be made, not found. That instinct is understandable. It is also wrong. Every element that triggers the disbelief has a documented origin. The impossible clarity comes from a spacecraft passing just 700-800 kilometers above the surface, close enough to resolve features 80 meters wide. The seamless surface comes from mosaics carefully aligned from dozens of individual strips, each with a timestamp and a pointing angle. The striking colors come from separate filtered exposures, enhanced to reveal the chemistry of nitrogen ice, methane, and reddish stolons that the naked eye would barely register. The unnerving smoothness of Sputnik Planitia is not a rendering artifact. It is a real plane of frozen nitrogen, so young and geologically active that convection cells churn its surface, erasing craters that should have accumulated over billions of years. The water ice mountains rising 3 kilometers high are real elevations, casting real shadows measured across real terrain. None of it was invented. It was recorded, packet by packet, across 4.8 billion kilometers, over 16 patient months of transmission at a few kilobits per second. Consider what this mission actually accomplished. A machine launched in 2006 crossed the entire solar system, threaded a narrow window past a world humanity had only ever seen as a smudge of pixels, and sent home images sharp enough to be mistaken for art. The disbelief is not evidence against the pictures. It is a measure of how far the achievement outran our expectations. What looks too perfect to be real is simply reality photographed by an instrument better than our intuition. The colors were adjusted. The perspective was assembled. The data was stretched to be legible. But the mountains stand where they stand. The heart glows where it glows. The plains flow where they flow. Strip away every enhancement, and the fundamental fact remains, recorded forever in reflected sunlight from the edge of the solar system. The terrain is real.